Good afternoon and welcome to the latest webinar presented by Advanced Thermal Solutions, Inc. This month's webinar is on the thermal management of automotive battery packs, and it is presented by Dr. Kaveh Azar, the CEO and founder of ATS and a world-renowned expert in the thermal management of electronics. Before I turn things over to Dr. Azar, I'd like to remind everybody that there will be time for questions at the end of the webinar. So if you have any questions, please type them into the section provided, and we will get to as many as we can at the end. Also, we will be continuing our monthly webinar series in November with a discussion of heat pipes and vapor chambers and their role in heat transfer. You can register at the same link that you used to sign up for this webinar, which is qats.com/training/webinar. With that, I will now turn things over to Dr. Azar.
Thank you, Josh, and greetings from ATS to all attendees. Thank you for your participation in this webinar. Let me talk about the electric vehicle battery thermal management review of options and technologies that are on the market. So the presentation is going to be at the understanding the lithium-ion battery working principles and how it compares to the acid-lead batteries, and the type of batteries that are deployed in the automotive industry. And then we focus on the battery thermal management from air, liquid, refrigeration, PCM, and vapor chamber. And I will try to bring it together at the very end with all the stuff that we see. As you're going to see, this presentation is benefited from the excellent work that's been done by many researchers across the globe, from Asia to North America. And I have benefited from the work that they've done. I've tried to put it together here for you to see what is happening and what's the state of the art as far as the battery thermal management is concerned. So starting with understanding the working principles of the battery, when we work with the lead-acid battery, it's a device consisting of two or more electrochemical cells that converts the stored chemical energy into electrical energy. So that's an essential function of a battery, whether it's a lithium-ion or lead-acid battery. In the lead-acid battery, current flows between the positive terminal, the cathode, and the negative terminal anode, isolated by a separator. Obviously, the cathode is at a higher energy potential than the anode. When the battery is connected to external circuit, electrolytes allows ion that's generated by the chemical reaction to move between the cathode and anode, and as a result of it, create the energy that's required. With the lithium-ion battery working principle, the lithium-ion cell stores the energy by intercollection of the charged lithium-ion in a graphite node, and then the cells are released energy, transferring these ions through an organic process and creating the current that we require to do it. When you look at the performance of the two battery types, you notice that the lithium-ion batteries are much more efficient in charge and discharge than the lead-acid batteries. And as a result of it, it's got a significantly larger acceptance in the deployment of the electric vehicles, not only electric vehicles, but a lot of the other battery requiring operations across the industry in order to function effectively. So it's a very attractive corner piece of the market as far as use and functionality is concerned, with a very broad spectrum. Obviously, when we get to electric vehicles, the demand on the power is significantly higher, and the issues associated with managing this thermal, as we're going to see, becomes more prevalent and significant. So what are the battery types? Two broad spectrum, or possibly three. It's cylindrical, it's in a gel roll or hard can, or it's wound or stacked layers or soft pouches. As you can see, examples of these that are shown in these applications. You see the example of a soft pouch or the can that we see that's very commonly seen in the industry. When we look at the inner structure of it, irrespective of the packaging that we have, whether it's cylinder, prismatic, or pouch, the inner construction of these batteries are identical in order for them to function effectively, as I showed you on the first slide. We have a negative electrode, we have the negative terminal lead, we have the positive electrode, and we have a separation or separator plate in order to make it function. And as you can see, these principles or these structure is common across these battery types and packaging. So obviously these are packaged for different purposes. So they have a application for, as I mentioned, a very broad spectrum from automotive all the way to laptops and so forth that we see. They use a similar type of battery or technology. When we look at the way the system is packaged in hybrid electronics, hybrid electric vehicles and so forth, we see overall packaging that looks like this, and from the outside it's got some connections, and both for power and cooling, depending upon the type of cooling that's used. If we sort of break it open, you can see that there is a multi-layers that are composing the overall battery that's used across the industry. But I think something is very important to notice in this schematic that's shown on the right-hand side is the thermal management is encompassing of the entire system. And there is a controller, as you can see from one of the researchers, what the important role the controller plays. But you can see that the sort of hierarchy of packaging as we go into the system. And there is a heat transfer and heat transport between different layers that has to be considered. So in a given application like this, not only we have to worry about the battery modules, we also have to worry about the ancillary electronics that's going to be functioning properly in order for the batteries to operate. So there is really two-pronged or 2 points of concentration as we go forward in the thermal management of our system. So we can't just focus on the battery. There is ancillary electronics that's going to be supporting the battery and battery operation that we need to know. So when we look at the type and the way it's composed and put together, you have in this case was a can, and the second case is a pouch or a plate. It's put into a module, from the module into a pack, and eventually into the vehicle. And we can see the example for the Tesla, for instance, the Roadster, that the way the battery is packed inside the rear compartment of the vehicle in order to provide the power that's required to go forward. And likewise, in the bottom, when you see on the Nissan Leaf, for instance, they have used the cells, and then they made a module. The module goes into a larger module that makes a pack, and eventually goes into a vehicle, but again, it's packaged differently. So you can see that the hierarchy of packaging is becoming more and more clear. And those of you who've been involved in electronics cooling, traditional electronics cooling, where we concentrated on the component, and in the component we focused on the junction. Here, our component is the battery, and the junction is the core temperature inside the battery that we have to be minimizing and making sure that's functioning at the level that's supposed to, in order to have a fail-safe operation with our electric vehicle. And the technology is all over the place, as very similar to what we see with traditional electronics packaging. It is very, very much system related, and the system in this case is a vehicle that we use as consumers, and the designers in these companies, they're putting the packages differently depending upon how the ultimate system is put together. You can see examples of the Chevy Bolt, Nissan Leaf, Fiat, Tesla, Focus, and Mitsubishi, on the IMIV. And you can see the packaging is totally different, and how they've utilized the system in order to put it together, in order to provide the energy that's required for the vehicle to be functional. And the reality is the mobility industry, not necessarily automotive by itself, requires a full range of lithium-ion batteries. It's not specific to one particular type. It depends upon the application and the system it's being deployed. But I think it's worthy to pay attention to this chart as well, that heat accumulation in the cell is equal to the net heat entering or leaving the cell plus the heat generation. And as you can see, heat accumulation in the cell creates additional chemical reaction, which is a problem. Heat from the chemical reaction accumulates in the cell, and any kind of a heat accumulation or excess heat that cannot be removed effectively, it could be a causal agent of failures, shortened life, and to catastrophic failure that we've seen some fires and so forth that's happening. So the thermal management, it is very much system related, and it's very, very broad across the industry. So what are the challenges with a lithium-ion battery? When we look at the issues with electric vehicle, the lithium-ion batteries have the best performance as far as the battery class is concerned. But they are very temperamental, and we have to be addressing that very accurately when we start to work with them. Key problems is dealing with heat generated by cell during the charge, discharge, and ambient conditions. This is the area of the menace we have that we have to attend to as we go through the design in order to make sure that it is done properly in order to avoid catastrophic failure. If our cells get too hot, 3 high-level problems occur: decreased battery life, decreased performance, and risk of fire or explosion. We have seen examples of fire happening with lithium-ion batteries at a variety of applications. We've seen it in the laptops. We've seen it on the automotive. We've seen it on the airplanes, depending upon where they were used and whether the thermal management system worked effectively for them or not. So when we look at the thermal runaway situation in lithium-ion battery, Halaj did a very nice graphic here to show what exactly happens. When we look at the ion battery, we have the anode layer, we have the protective layer here, we have the electrolytes and the separator, and then the cathode layer. And the first thing, when the heating starts, this is area number 1, then the protective layer breaks down, and electrolyte breaks down into a flammable gas or gases. And then the separator starts melting, possibly causing a short circuit, and then cathode breaks down and generating oxygen. So we have all the components for a catastrophic failure if we have this thermal runaway that is not managed effectively in our system. And the net result of it is here. What this picture shows, I believe this is from 3M, if my memory is, yes, it is 3M, where they're showing the difference between an immersed battery pack into a liquid versus unimmersed, and you can see where the fire occurs. And in the 3M Novec fluid, you can see that's a better containment of the thermal runaway, and the issues could potentially happen with it. Whether this is practical or not, it is a question that we're going to try to address as we go forward. But nevertheless, it shows that if we manage the thermal runaway or during the charge, discharge, or possibly extreme ambient conditions, we could have catastrophic failures, and there are solutions to address that. So what are let's start at the thermal management. We know that lithium-ion batteries could potentially cause fire and sometimes explosion. We know we have oxygen, and oxygen is an explosive gas. So how do we go about managing this from a thermal standpoint? What are our options? What are the people have done? What are the things that people have done in the industry in order to be able to address this? I think it would be helpful to just take a look at and see what are the different options and compare it against the internal combustion engine vehicles and see what the changes are as we go from internal combustion engine to electric vehicle to hybrid systems. You can see the cooling system. I apologize if these pictures are not very large. I tried to put 3 of them into one sheet so we can have a ABC comparison. And you can see that the overall structure with respect to the evaporator and a condenser and some sort of a heat exchanger here continues to be the same across different industries, vehicle design. And obviously, as we go to the hybrid vehicle, we can see in addition to the battery, we have the engine here too that we have to also worry about from the thermal standpoint. Not only that, but also from the thermal coupling that could potentially take place between the internal combustion engine and the battery compartment. So the problem with the hybrid could potentially be twofold, depending upon the packaging that we have. Obviously, when we go to the pure electric vehicle, some people call it a plugged electric vehicle. You see this PEV or PHEV being used interchangeably. It's a both reference, so however we come to the conclusion. In this particular case, there is no internal combustion engine, and the vehicle is purely driven by the electric power that has to be charged, obviously, from the electric source. When we look at this overall thermal management, there are some conditions that we have to address. It's a load profile, current rate, short circuit, and over voltage. On the environmental side, remember what we saw from in the typical electronics packaging. We always go from the environment to the junction temperature. We never go from junction to the environment. We have to address the environment. And in electric vehicles, it's no different when it comes to the battery management. We have a system that we have to address, and we have to come all the way down to the core temperature of the battery. So the environment plays an important role. Ambient condition, ambient and coolant temperature, contamination, altitude, climate. Remember, these are also the issues that we deal with when we deal with traditional electronics cooling. And equally as important, because of the fact that standards in any industry, automotive obviously is very known for it, and it's no different. So existing ecological laws and safety issues are huge. You don't want to have a passenger car catching on fire and harming people. So when we go to the levels that we saw, how the system is packaged, it is the cell, pack, and the system. We see the issues that are associated with that is the chemistry, geometry, reactions, and properties. On the pack is a thermal interface, which is huge. And you're going to see examples of how the interface makes a difference, especially when we come to phase change material. Coolant medium, coolant flow, whether it's liquid, forced, natural convection, what have you. This all happens at the pack level. And then the system interfaces between the packs, optimization amongst packs, and then realization of the intelligent algorithm. And you're going to see examples of this, that because of the fact we're dealing with a chemically active system, we cannot really walk away from the intelligent algorithm to make sure that the system is being monitored and controlled, and the electronics associated with that and their thermal management is a huge point of concern that we have to address. So when we look at the lithium-ion battery, this graph on the top clearly shows the superiority of the lithium-ion battery in comparison to the lead acid and other types of batteries that are in there. And depending upon the energy density that we have and the type of vehicle, you can see that the power density changes quite a bit. It depends upon the usage. There are two other components that we have to pay attention to, in addition to the power density requirements and so forth. That is the safe operation of the battery. There is a point of as a function of temperature. Notice that these are all function of temperature as we are talking about it. The battery power and temperature, when the temperature ranges between about 20 to 40 degrees C, we have a peak performance. So if we can keep our batteries at that temperature range, we have the best performance, the best return on our investment as far as charging and discharging is concerned. And equally as important is the expected life. There is a very, very much of a temperature range where these devices function at a most optimum, so we can get the longest life. Remember, there are requirements that we have to meet in order to be able to have a product on the market that's going to function effectively. Otherwise, people have to go with their vehicle to the dealership and change the battery every 2 months. So what is the overall map of the thermal management concerns that we have to address? So when we look at this, the temperature effects are the operating limits, life cycle, and this is you're going to see this number modified, massaged by different researchers, and the thermal runaway, which is a huge problem, and we would like to avoid as a result of the thermal management. And the sources of heat and sinks are electric heating. We have the Joule's effect that happens, and we have to manage effectively thermochemical heating and cooling that takes place, and external thermal effects that always impacts the system as far as the environment is concerned, whether you're driving in say, Arizona in July, July 22nd, or you're in Alaska in Juneau and driving in wintertime. So the electric vehicle or hybrid, large size batteries, high thermal capacity, high heat dissipation requirements, low temperature rise. And again, the low temperature rise is important for the functionality of the vehicle as well as the safety and the longevity of the battery. On the hybrid vehicles is a smaller size of the battery, low temperature capacity, low heat dissipation requirements, and high temperature rise as a result of it. Again, high temperature rise is an issue. So the temperature control prevent from overheating, heat dissipation at higher rates, uniform heat distribution. This is very important. Again, those of you who've been involved in electronics cooling, when you put the stack of PCBs right next to each other, you see a temperature gradient across that, and the batteries are no different. The batteries are effectively, for the sake of analogy, are individual PCBs that we put right next to each other, and we need to make sure that there's a very, very strong temperature distribution uniformity across these. Otherwise, we're going to have neighbor heating taking place, and as a result of it, all kinds of thermal issues. So self-heating elements, external heating, thermal insulation, and so forth is required, and also the heat recovery. And some people are using the heat also as an energy source to possibly recreate if they can, but that adds additional payload to the overall vehicle. So as a result, thermal management is not a singular point that I can say, okay, I just manage the temperature of the lithium-ion battery. I don't have to worry about anything else. But no, it's an integrated system. We have to address all aspects of it and be aware of it as we go through the design and make sure that the system is designed properly. As I mentioned, there is industry standard that are communicated because of the fact we have a human interface. We have a device that interfaces with human and occupies, or people occupy the space. One of these standards is a Freedom Car that is targeted by 2020, and there are all kinds of expectations about it. But some of the sort of highlights are 55 kilowatt for 18 seconds, which is a tremendous power surge that we have to manage and have. Continuous power of 30 kilowatt. And imagine in a confined space, this is a tremendous amount of power that we have to maintain, manage, or generate. And equally as important, the daunting task of 15 years of operation of lifetime, or 150,000 miles. This is not a trivial task. Those of us who are a little bit old-timers, we know when you design for a long life, it's a very, very challenging process, and you got to make sure that all the components that are used in that system are meeting the requirements that are associated with that. I'm not going to go through all these details, but just to highlight what the Freedom Car thermal goal is, dissipate 200 watts per square centimeter. And just to get a sense of what this means, if you look at your sort of pinky finger and look at your nail on your pinky finger, that's effectively if you put 200 watt light bulbs on that area. That's almost 1 square centimeter. So you can imagine that the thermal concentration, or the heat density, as I hate to call it, is very, very severe when it gets to that level, and we need to be able to manage that effectively. And coolant temperature of 105 degrees C for the maximum junction temperature, or battery temperature of 125 degrees C. These are very, very critical numbers that we have to meet with a challenge that we have to make sure that it is delivered. So what are my cooling options? I'm dealing with potentially a significant problem. It's a challenging from the thermocoupling standpoint and the packaging standpoint. And when we look at the options that are available in the industry that has been either deployed or accepted, are effectively, in a broad sense, are air, liquid, and refrigeration. So when we look at the air cooling, both cooling and heating is feasible, good performance, normally large space needed. It's the cheapest, certainly, like any other electronics cooling. Lower development efforts is needed, certainly, for these applications. Liquid is the lowest temperature gradients, and please pay attention to this column right here with respect to the liquid and with refrigeration. When you look at the air, you see a significantly larger temperature gradient, but when we look at the liquid, it's 1 to 3 degrees C. Now, remember what I said a little bit earlier, is the uniformity of temperature from pack to pack, or from battery to battery, is really, really important, so we don't get the neighbor effect as severely as we have seen in other applications. And refrigeration is aggressive, cooling due to very low cooler temperatures, intelligent thermal management, and a specific pack design needed to avoid a too aggressive cooling and condensation of humidity. Irrespective of the type of system with deployed refrigeration, the condensation is a huge point of concern, and its management could potentially be very, very costly. So you can see that these products or systems have been deployed or are being contemplated to be deployed in different electric vehicles, and as a result of it, we have options that are utilized. So before we run into the options and review those with you briefly, I'd like to just go over some of the thermal stuff and see some of the data that you're going to see where they have come from. I know we're dealing with a chemical process in lithium-ion batteries. For a lot of us who are mechanical engineers, that this could be a sort of a point of ambiguity that, what is it that we're dealing with? Obviously, we're coming out of the battery. We're trying to maintain the core temperature. We're dealing with the surface temperature. And when you look at the heat transfer equations that are associated with that, is very, very straightforward stuff that we've done over and over again. You can see that there is the fin temperature here. In this case, I use the example of IGBT, but it could as well be a battery. It doesn't really matter. It is a point of describing what transpires and what are these interlayers that we have to worry about. Whether I put a battery in there or IGBT, there are layers that interfacial resistances, interfaces that we have to manage effectively. So you can see that for instance, the convection losses that we have through the fin is HA TB minus TC. Obviously, m.Cp is also a function of that. These two hand to hand in order to be able to take the heat away. And the T hot, the silicon or battery temperature divided by the fin temperature, which is the highest delta T that we have, is a function of all these resistors that we have to manage. And these are irrespective of what we are putting as a cooling system, we have these interfaces that we have to account for, and if we don't if we don't pay attention to them, it could come back and adversely impact our design or positively impact our design, depending upon what you miss. So this effectively shows by us trying to manipulate these. For instance, if I change the value of H, I can significantly impact it. If I change the mass flow rate, I can impact the total heat I'm transporting through the system. If I change the fluid, this C sub P, I can also again impact the total transport capability. Remember that m dot is equal to rho v a, where a is a cross-section area that the fluid is being taken away. So if I change the cross-section area, optimize my heat sink, if I change the velocity, if I change the fluid type, all of these is going to impact the total heat that I'm transporting. By looking at these interfacial resistances or material resistances that are between the source and the sink, I can again further optimize my thermal transport capability. A smaller that resistance, larger the Q2 that I can take the heat transfer into the heatsink and take advantage of it. We see Abraham did a very nice job in showing the capability of these packaging as it applies to electric vehicles or in general the cooling of the IGBTs. And this is really done for the demonstrative purposes to show, for instance, if I have a heat source and a heat sink, what are the capabilities that I have? What if I put jet impingement, meaning the fluid is being impinged in the bottom and on the top? What do I get? What if I put microchannel heat sinks that have a very, very high thermal transfer capability, but at the same time they have a very high pressure drop, so I have to balance those together. The points to remember, our target is 200 watts per square centimeter. Our temperature is about 105, and the coolant temperature 105. Then the hottest temperature T sub H that's associated with this assembly is at 125. Anything that falls in this area is a possible solution for me. And the important thing to look at it and bring it down to this axis is the effective heat transfer coefficient. You can see that this is from effectively about 30 to about 80 kilowatts per meter square degree K. This is 40,000 watts per meter square degree K. All of us who've done some heat transfer work, we realize that this number is a daunting task to achieve. Is it achievable? Absolutely. So there is a solution out there. as we're going through the design and limitations, we have to understand what it takes for us to be able to get to these temperatures and be able to deliver this level of cooling system that's associated with that. But you can see certainly it is a plausible and possible, the different applications that you have. And as you change the fluid, you can decrease your heat transfer coefficient value. As you change the velocity, et cetera, as we talked about it before. So air cooling, there's a very nice work that was done by Tao that he showed the effectively the governing equations that we have in order to be able to simulate and understand what happens in a battery cooling if I want to do it by air. And then he uses the Nusselt number and the Reynolds number as shown here for a specific battery pack that we have to use. So you can see the SOC is the state of charge, and SOC naught is the initial battery state of charge, whatever capacitance has. But I'd like to point your attention to the equations and the kind of information that we can get out of it. As you've heard me say in the previous webinars, I call this integral modeling. That we can very quickly get a good estimate as to what is happening in our battery system and where are the points of concentration that I have to worry about, and do the parametric analysis. This can easily be done in any of the available tools, from the Excel to some like MathCAD, MATLAB, name it, it's available on the market that we can get, and Mathematica and so forth, and solve the problem. So having these governing equations, he did a very nice job in looking at the performance of the what happens in the system. He did something like 37, 38 different simulations and changing the variety of parameters. I am only showing 3 of those, that just to show the capability and the kind of things happen as a result of the modeling, and then the points that we have to pay attention to and manage. This is the system that you have the bunch of batteries and the air is coming from the outside and leaving the system. So the T sub C, the battery core temperature, is obviously the most important point. This is the one that's shown in the red as to what happens to it. This first one shows the backstabbing controller that he had deployed as a parameter shown in these equations that are being controlled with as a function of time. And what you can see is the core temperature is very, very stable throughout the process with putting the controller. You remember I pointed out to a circuit board in an earlier slide and said we cannot ignore the electronics that we have to deploy in order to be able to solve the problem. Without this controller, this wouldn't happen. But you can see the surface temperature fluctuations, and you can also see the coolant temperature or air temperature fluctuating quite a bit in this case. Now, when we come to a fixed cooling temperature, that means there's no controller involved. You can see that the sort of the onset of the temperature rising very rapidly and going over the 40-degree limit that we had. Yet the surface temperature and coolant remain very stable. When we go to the linear optimal controller, we can see a little bit of a fluctuation in temperature, but the delta T that we see in this is very small, in the order of 1 or 2 degrees. But we see a higher level of fluctuations in the air temperature and the surface temperature. This may not be attractive in your application, but nevertheless, very simple set of equations is enabling us to understand and the dynamics that's required in order to manage the system by air cooling, and what are the salient points that we have to worry about and pay attention to. In your given application, for instance, this could be perfectly functional as long as you know that this is going to stabilize and not go any further. Going over 40 degrees C, as you saw, it is not a very ideal situation for us to operate, as it's going to start impacting the battery performance and life as a result of higher temperature. So the next cooling method is a liquid cooling. And again, I try to show here what are the options that we have as far as the liquid cooling is concerned with different systems that are deployed in the market. Yes, you can see a passive liquid cooling system where we have the air coming in to the liquid to air heat exchanger here, and there's a fan that's exhausting into the ambient. But nevertheless, this is the cycle that you have in order to be able to manage the cooling. So this could be an application for a not necessarily electric vehicle or maybe a light electric vehicle, one of these smart cars that are very compact and small, effectively glorified motorcycle. So active, moderate, liquid, and heating that may be required. And again, you can see that the presence of a liquid to liquid heat exchanger, and this goes into the vehicle coolant that comes in and take advantage of the vehicle coolant. So active cooling and heating, we have the air from the evaporator or refrigeration from the condenser comes in. We have a heat exchanger placed here and the liquid to air heat exchanger. So the problem gets more complex and more components have to go into the system, that we have to address the reliability, we have to address the weight issue, we have to address the cost issue, and also its effective management of the battery pack, depending upon what we have to use. Ultimate objective is to make sure this battery pack is working properly and it's giving us the performance that we want. So when you look at the level of packaging that takes place, this is an example from Audi that they've done. It's you can see how complex the process is. You have the cells that are shown here, and this whole assembly is put into this structure that has the lower protection cover, has the cooling system, as you can see in the middle, with the fluid coming in and going out. You have the battery frame, that the battery has to be held intact, and housing tray in order to be able to accommodate the batteries and so forth, and the aluminum crash structure in order to make sure that they're protected in the case of possible crash. And then you can see how these are going from here and packed into this, and then eventually into this system, that the plumbing, all the packaging that's required in order to make sure that this one complete unit for transportability. You can see that as we talked about it before, the serviceability of these batteries are very, very important. And you either want to have one battery that you can pull out and put a new battery in, or be able to uncover this and change the individual cell or two that may have stopped functioning properly. And eventually this whole thing goes onto a chassis that powers the vehicle to go forward. And some of the vehicles that we see on the market right now, they have quite a bit of power, quite a bit of range, to 300 to 400, depending upon obviously the weight of the occupants and what's inside the vehicle. But they can go at the high speed in long distances. So the battery technology has really transformed quite a bit. The cooling technology, in this case liquid, has also transferred quite a bit in order to be transformed quite a bit in order to be able to support that level of functionality. So when we look at the liquid in this example, you can see the schematic we have the battery cells here, and then we have the cooling plates that are in gray, if you can see it on your screen. And this is one embodiment, if you will, one design. And eventually these are coming to the connections to be able to circulate the liquid and take it out. This is a design, the one in the bottom, that was done by Tesla, where you can see that there is a tube that is being drawn right through the battery pack, but there's a connection between the battery pack here and the plate. And again, this is a patented technology by Tesla. So you can see the different embodiment, different implications that are done in order to be able to cool the batteries. The objective is to make sure the batteries are maintained properly. And I'd like to draw your attention to the number of batteries that are being used in this particular application. For Tesla, 18,000 batteries are used in this application for the Model S battery. And again, more deployment of the liquid cooling, and I like to again draw your attention to the complexity and how designers have gone about to design this very effectively. What you see here is an example of a Volt by I believe by Chevy, where you have the battery, you have the fin plate, and you have the cooling plate, and then this area is attached to the coolant that's being circulated within the battery pack. All of these are put into these plastic frames and packed together into a structure, and eventually is packed into this. But when you can see, as you can see here, there is inlet and outlet for the glycol material fluid to circulate inside the system to provide the cooling that's required. It's a very, very effective system, as was designed by Chevy or GM, But you can see the complexity that they have to go through in order to be able to make sure that that the connection is made. Notice that every single one of these effectively is a fluid connection joint that has to be effectively sealed and make sure that's functioning properly with the expected life that we talked about. We're talking about a seal that's supposed to last 15 years in elevated temperatures with shock and vibration and extreme temperatures, and be able to function effectively and not provide a leak. The next concept for cooling that's been explored by some manufacturers is an old concept. It's called the immersion cooling. In the old traditional immersion cooling, you just dropped your electronics into the bath, and there was a heat exchanger on the top, where as the fluid vaporizes, it condenses and comes back. So there is a full cycle taking place in there. This concept found its way, I think initially was designed in the vacuum tube era. And then in the 60s and 70s, mainframe computers like IBM and others started exploring this possibility, and was never really successfully deployed. They kept on coming back to a less cost-effective, less costly, I should say, systems for cooling, and deployed it accordingly. And now you can see it's being possibly contemplated in the battery cooling, where you can put your cells inside a container, and you have the liquid cooled heat exchanger on the top, where the fluid turns from vapor to liquid, and the cycle is repeated over and over again. The biggest challenge obviously we see is in the packaging and serviceability and repair of these parts as you go forward. Here is a concept that's done by I think Zeng modular battery systems out of China, that they're putting the whole system into a immersion bath, and this is what these systems look like. And you obviously have to have a liquid to air heat exchanger in order to be able to take the heat out if you don't have that heat exchanger on the top. But irrespective, you have to have that another heat exchanger further back to take that heat that you generate by the battery in order to make sure they're working properly. 3M Novak that we talked about before, they obviously claim that this is a very effective cooling system, and that they have highlighted the benefits of these, as a direct cell contact helps improve heat transfer performance, help improves pack temperature uniformity. I mentioned that this is very important, and certain liquid cooling or immersion cooling can helps protect against cell-to-cell thermal runaway, which is the neighbor effect that we talked about. Potentially enables a higher charge and discharge rate because of the fact the whole system is at a lower temperature. If you remember the chart that I showed you that said for the liquid cooling, the temperature gradient is between 1 to 3 degrees C. So the successful design requires a liquid to air heat exchanger or an active cooling system in order to make sure that we can remove the heat and create this recirculation that's required. And we have a change of the phase change takes place from vapor to liquid, so we never have a dry out. If your liquid to air heat exchanger fails, you're going to have a dry out. So all the liquid inside the immersion system is going to vaporize, and as a result of it, we may have all kinds of catastrophic failures. Certainly, heat pipes have been used in a variety of applications, and automotive battery cooling is no different. We all know that the heat pipe is a transport mechanism that takes the heat from point A to point B, and they come in a round and flat shape, and they've been certainly deployed or considered in the battery cooling. No different than any other application, where you have the heat source and you bring it out to an area that you have a better airflow, and then you put the fins on it, excuse me, in order to be able to cool the batteries and take the heat away. So in order for this to function effectively with or without the heat pipe, is you have to have an effective heat sink at this end of it. Otherwise, your system is not going to function effectively. The same applies, excuse me for 1 second. The same applies for the cells, the can cells and so forth. If you put it inside a container, and if the container is filled with some sort of a transfer fluid or medium, you can take the heat away and use the flat heat pipe to dissipate it elsewhere. The heat pipes do two things. Number one, they transport the heat very effectively from point A to point B. Number two is it allows you to spread the heat more uniformly over your entire surface. In the back of your heatsink, if you have heat pipes, you can get a better distribution, and so you can use your heatsink more effectively. So you won't have hot spots on your heatsinks as a result of it, less effective cooling that takes place in there. So phase change is another thing that has been socialized or contemplated for a variety of applications. What a phase change material is, it's like a paraffin or some sort of a wax that changes phase from one state to another, from solid to liquid, from liquid to vapor. And as long as the cycle is repeated, we are all set. You can see here that there is a storage temperature as well as the capacity to retain heat and the increase of the internal resistance, which is another something very attractive that we want to see. And we can see the temperature dependency. Temperature dependency affects both parameters that are very, very important in the phase change. Wang had done a very nice study to show what happens to these devices as we go forward. So he used PCM that was pure paraffin. Then he changed it to the expanded graphite and paraffin, some mixture of 20-80%. And then he chose the third one that was expanded graphite, epoxy, and paraffin. And as you're going to see, epoxy has other advantages that provide some consideration. So this is the setup that Wang looked at, and you got to look at the also functionality of the PCMs or phase change materials, that you need to have active cooling in order to be able to return it to original state. So the first one, the blue dots show the pure paraffin. The red dots or red markers show the 80-20 combination, and the black ones show the third combination, where there's the epoxy, paraffin, and expanded graphics. And as you can see, obviously, the lower the temperature, better off we are. But equally as important, please pay attention to the cycle. The time that is changing as a result of it when we change the mixture and the combination. So it's a highly transient problem. The combination of the mixtures that we have, depending upon the discharge, at 3 different levels. That's discharge 1, discharge 3, and discharge 5. And this shows the discharge rate and also the temperature difference. And the green one shows no cooling if I had just a standard cooling process. And you can see that the composition and the mixture that we have plays a significant role in the effect of PCM. So let me not go through these details. You saw the numbers that you saw with respect to what the temperature fluctuations are and what the gain and benefits are, to upwards of 20-30% when we change the mixture. But important thing, let me just do these observations. Battery thermal management using PCM shows excellent performance in limiting peak temperature at short periods. So when I say that conclusion, the thing that comes to my mind is PCMs are certainly good as a sort of a safety valve. I have a cooling system in place. I'm going to put additional PCM in there in order to make sure that if I have a thermal runaway, at least I have a secondary system to suppress the peaks and manage it effectively. The battery using PCM without convective cooling methods may not be practical at all. We have to have a cooling system in order to be able to bring it back to normal temperature. The use of the PCM in those applications enables us to use a smaller air cooling application and bring it to a reality. And lesser the weight, more effective our devices, and vehicle designers will need to weigh the potential increase in mass and the cost associated with PCM against the anticipated benefits. We at ATS have done use of the vapor chambers to be able to effectively cool these batteries. What we've developed is an array of aluminum and titanium vapor chambers. Vapor chamber, for those of you who may not be familiar with it, is effectively a flattened heat pipe. Effectively, and what we've done very successfully is been able to, I lost my pointer here somehow, to make it out of aluminum and titanium, but in very large sizes, and able to put a cold plate and or heatsink on top of it. Whether this is an individual system or connected to the bigger system, doesn't make any difference. The point is its ability to have a very large platform that can rest against the batteries. You still have the thermal interface materials, but what the vapor chamber does, it uniformizes the temperature gradients across multiple batteries, and then you have the dedicated cooling system to be able to take the heat away, and or put it into a bigger system. So you can see there is a broad deployment of batteries in a variety of applications across the industry. So whether we have done automotive or whatever that's a point of concern, you see that the batteries are being deployed. And the point that we have to pay attention to as we go through it, like other electronics that we've dealt with over the years, deployment is very much system specific. We cannot take the system that's done for company A and just plant it into company B because of the fact that it is very much designed for the final application that we have to go through. So in summary, temperature and effective management play a key role in deployment of battery system in any application, including electric vehicles. Two major problems caused by temperature can be found when it comes to battery cooling. One is the temperature exceeds permissible level during the charge and discharge, and uneven temperature distribution attributes to localized deterioration of the battery and potentially catastrophic failure. Temperature affects heat source and heat sink, electric hybrid vehicles and batteries and so forth. The temperature control should be considered before designing the battery thermal management system. It is very important that we have that information in front of us before we go and design something that's not going to fit effectively. Either low for less than 15 degrees C or higher temperature greater than 50 degrees C will adversely reduce the battery cycle life, and that's very effective. Remember, the batteries that is expected to be designed by the Freedom car supposed to operate for 15 years or 150,000 miles. Research suggests that lithium-ion batteries, the desired operating temperature to achieve required safety and performance is between 15 to 35 degrees C, with 5 degrees C temperature variation from module to module. A daunting task. It's not an easy thing to attain if we especially don't have the proper resources in order to make sure that we can design the cooling system that's going to fit the application. Ladrich and his team provides the following temperature bands at different operations level: battery capacity and pulse performance from 0 to 10 degrees C, optimal range 20 to 30 degrees C, fastest self-discharge at 30 to 40 degrees C, irreversible reaction and short circuit between 40 to 60 degrees C. And there are three primary cooling approaches that are considered for the battery thermal management at this junction: air, liquid, and refrigeration. And every single one of them have branches that are associated with that. Air cooling could have a PCM, heat pipe. Liquid cooling could have a PCM and some sort of a system level cooling, refrigeration, etc. So design of the cooling system is a strong function of the final product that will be residing. Cost of the ownership is very, very important. A lot of us we don't pay attention to it as we're going through the design. It is not just the cost of the battery, it's the service life, access to parts, operating expense, and all the way to disposal and every other thing that's in between, among other parameters, are important consideration once considering a design of a cooling system. So it's not we don't want to design in a vacuum. We want to understand what's going to happen at the end, and the users are going to use it in order to make sure that we have designed an effective system for it. Similar to any other electronics cooling problems, there must be a technical or marketing reason to go to a higher capacity cooling. Always start with air cooling and travel up the cooling ladder to make sure that you have exhausted the options that are associated with the cheaper, less complicated systems like air cooling before we go to liquid. And as we go from liquid to refrigeration, it gets that much more complicated. One thing that's really important to know is that the market is rich to saturate it with design and cooling options for battery thermal management. We need to see the do's and don'ts because there are a lot of stuff that's been done. There's so many articles, so many presentations, and so many conferences and so forth dedicated to this concept. People are doing all kinds of work across the globe. Before you jump into a design, please take the time to understand what has been happening and what's the best thing that you can do or you can learn from what's been done. But the do's are review and understand the problems and the boundary conditions that the solutions or the solution was developed for. Understand the approach that the engineer took to solve the problem at hand, not just the final system. The don'ts are, do not assume that the solution is an end-all, meaning since it worked for their product, it will work for your design. Do not copy what they did. Solutions published are very problem-specific, and they speak to the possibilities, not the exact solution. We can learn a lot from our colleagues who've done, and when you come up with a nice design, if your company allows it to publish it, please share it with the community. I think it's always very valuable when people publish their work, and as long as it's not proprietary, and get the technology communicated. But something that I've advocated all the time, two solution approaches, whether numerical, analytical, or experimental, are fundamental to the solving BTM issues. They are no different than any other thermal problems or engineering problem that you solve. You have to have two solutions. An accurate estimation of the battery core temperature, like the A6 junction temperature, is the core focus for developing an effective cooling solution. There is no difference between the junction temperature and the core temperature that we've done with the batteries. These are all the same. We have a temperature that we have to maintain, and you saw the important role the junction temperature or the core temperature of the battery plays in its expected life and the performance. So with that, I thank you. ATS has been around for almost 30 years. We provide mechanical and thermal design services, cooling solutions, air, liquid, and active and passive, instrumentation and wind tunnels, manufacturing services, training programs, and QPDA. So with that, I thank you for your attention, and I'll be more than happy to answer any questions.
Thank you, Dr. Azar. And we do have one question that has come in. The question is, what are the major advantages and challenges associated with two-phase immersion cooling?
The biggest challenge with two-phase immersion cooling is the same thing that we've seen in the high computing industry, or the vacuum tubes, which is way back before that. The issue is the issue of packaging, issue of the thermal runaway, making sure that the cooling system that the heat exchanger that I showed on the top. Let me see if I can go back to what I had, so I can point to it effectively right here. If this core is not working effectively, this combination, all the liquid is going to turn into vapor, and you're going to have a dry out. So you're going to be dissipating all that power, and you have no effective cooling that takes place inside the system. So the challenge is the packaging. It's a control. It is serviceability. What do you have to do if you want to change the batteries in here? How are you going to fill the system? How are you going to change the fluid? Is the fluid now, as a result of the functionality, environmentally safe? Disposal of the fluid. So all of those things. Every system has its own challenges, but from the thermal standpoint, making sure that your heat exchanger is working effectively and the condensation is taking place. That's the biggest thing. So whatever is residing at the end of this system to take this heat away, this has to function perfectly at all time. You have to have a shut-off system here, meaning if this failed, the controls that we talked about, the system is shut down. So it doesn't work anymore. So those are from the thermal standpoint. The other part of it is the deployment. When you deploy it, I'd love to see how this is going to be changed or done in a service area. If you have to go back and fill this cavity or this bathtub with fluid again, and how you're going to be doing it. Very effective, very difficult, very expensive.
Well, thank you for everyone who's joined us this afternoon. If you do have any other questions, you can feel free to try to type them in. Just a reminder that our monthly webinar series will continue next month in November. I believe it's November 29th is the exact date, and that will be on heat pipes and vapor chambers and their role in heat transfer. And you can sign up and register for that webinar at the same link that you had registered for this webinar as well. I'm not seeing any other questions, so I just want to say thank you to everyone who joined us, and thank you, Dr. Azar, for the presentation, and hopefully you'll join us again next month.
Thank you.